All right. So you're going to get going on solving an actual momentum problem today of a little more complication. So you have done some pretty straightforward momentum problems, like P equals mv. Here's the mass, here's the velocity, find the momentum, etc. All right, so let's break this down because it gets richer. It actually gets very powerful. By itself, that doesn't tell us too much. All right, what if F net equals 0? What are we talking about here? Based on the second half of the impulse equation, notice we're on notes page 19. Here's the impulse equation. J equals, write this on the top of your paper. You should write everything I write down here. F net, I'm writing so slow, this should be very easy for you to keep up. F net T, that's the fat, equals delta P. And don't forget, the one that's not written in your reference table, the MAV, M delta V. Okay, so if we look at this equation and we ask the simple question, look at just this piece. F net T equals delta P. And we ask a simple question. If F net equals 0, so if there is no net force, then, of course, if F net is 0, look at the equation. This whole term will be 0, then the change in momentum must be 0. Which means if there's no change, it means momentum, well, there it is. There it is in English. Here it is in symbols. Momentum doesn't change, which means momentum is constant. Now, don't let this get exciting like, oh my gosh, what is he talking about here? This is Newton's first law. This is objects at rest will stay at rest. Objects in motion will stay in motion at a constant velocity unless there is an unbalanced or net force. So all this is saying is things keep doing what they're doing. So it's the same thing here. If there's no net force, this is literally Newton's first law just done backwards. So we start with the fact that there's no net force. Well, that means that the object has to just either stay at rest or stay in constant velocity motion. Of course. Well, since momentum is mass times velocity, if the velocity doesn't change, and of course the mass doesn't change, well, then the momentum can't change. So remain the same, remain the same, remain the same. All this is saying is Newton's first law, but we're just switching up the symbols a little here. You see we start to play this game more. Another way to say this, which is exactly Newton's first law, if nothing from the outside interferes, the momentum will remain constant. But notice here, I've slipped something in there. I've slipped this comment, or a group of objects. Now, we've been doing this object at rest, stay at rest, object in motion, stay in motion. We've been focusing on one object, like a block sliding across the floor, or whatever it is, or a spaceship moving in space. But here, could we extend this to more than one object? Well, yes, but we'll get to that in just a moment. All right, here's just some terminology for you. When a physical quantity, like momentum, velocity, whatever it is, when it remains constant, it is called conserved. Now, you've probably heard this. Conservation of energy, I'm sure you've heard of. Conservation of momentum, which is what we're introducing here, you may have heard of also. But whatever it is we're talking about, in this case, it's going to be momentum, it is conserved. That means its total amount remains the same. It is constant. Now, it's always under a certain set of conditions. Always. It's not like, oh, look, there it is. Momentum's conserved. No, you have to define what's going on. In fact, what you have to define is a system. This is true. All these comments right here, all this comment right here, momentum will be conserved or stay constant within a system. Let me add this all the way over here. Within a system. Within a system is a fancy way of saying, I'll color code these things. It's a fancy way of saying within a system is just a physics way of saying nothing from the outside interferes. These two are the same thing. Nothing from the outside interferes within a system. If that's true, there's an equation in your reference table. It's a really easy one. Here's your reference table. Let's pop that out. Come on down over here. Boom, here it is. You see it? It says P before equals P after. Now, though that looks like perhaps the simplest equation on all of page 6, it carries quite a bit of richness. It's very powerful. So actually, that's what we're going to write here. That is the law of conservation of momentum. P before equals P after. P meaning momentum. P meaning momentum. Before and after is actually a time command. Before a certain event and after a certain event. So there must be some time that elapses. The before and the after are going to be very important. In fact, those are perhaps the most important part of getting this right. So I'm going to underline before, after. Do not make the mistake of just writing P equals P and keep it moving. You must pay very close attention to the before and the after. Now, there's a second video that's going to give you page 20. You're going to do the example on top, and then you'll do some practice. That will really stress this, but keep it in mind right here. Before and after is a time command. It is before some event, after some event. So you have to have time elapse. Something needs to happen here. All right, so let's get over here. Let's get into this. We are essentially going to focus today on just this problem. Conservation of momentum is useful not for one object. For one object, if there is no outside interference, nothing changes. So there's nothing really interesting to discuss. If it's sitting at rest, it stays. If it's in motion, it'll stay at that same constant velocity, same direction, same speed. It gets interesting when you start looking at two objects or more. We'll stick to two. A nice one that we started looking at yesterday, we watched a couple of videos, is the explosion problem, such as firing a gun, firing a cannon. We saw these two. And actually, there are other explosions too that we didn't yet talk about. Throwing a shot put actually counts. Doesn't have to be fire and brimstone. Explosion just means two things that start together and push apart. Even a spring-loaded gun, a little rubber band gun or something, all of these things qualify as explosions. We'll generally tend to focus on firing a gun or shooting a cannon just because they're very easy to see the explosion. Anyway, let's check this out. This that we did in the hallway yesterday, our cannon and tennis balls, our tennis ball cannon, this is a good example of a conservation of momentum problem with two objects that explode. So if you notice up here, we have object 1 is the cannon, and object 2 is the ball. Now, this comment within a system, aka no outside interference, is very important. What that means is the only net forces that are going on in here, the only forces going on in these are the cannon pushing the ball this way, really it's the gas that explodes, and the ball pushing back on the cannon this way. There's nothing else from the outside, like my hand is not actually grabbing the cannon. If it were, we would no longer be within the system, or we would have to expand the system to include me, and then it gets messier. So here, the only two things pushing on each other are the cannon via the gas is pushing on the ball, and the ball via the gas is pushing on the cannon. This is what we call a system. If this is true, if these are the only two things influencing each other, then this whole system, we can say, has a net force of 0. And it does. Actually, if you added everything up in here, you would see that. You would say, oh, the cannon has a net force backwards. Absolutely. The ball has a net force forward. Absolutely. But those two forces are equal and opposite. So if you look at the whole system, both objects together, the net force is 0. So the change in momentum for the whole system should be 0. So the momentum should be constant for the whole system. That's the context of using conservation of momentum. So how do we actually do this? It's actually pretty straightforward, but you must follow the process. Break the problem into two halves. I want you to write it out just like this. P before equals P after. Now, how will you know to even do this? Basically, if you see an explosion problem and they start giving you masses and velocities, then you're probably doing conservation of momentum. Now, this is a key step. Before the explosion, there are two objects, the cannon and the ball. And so I will come over here and say, well, before the explosion, the momentum of object 1 plus the momentum of object 2, sorry, here we get a little overlap into the lower part, object 1 plus the momentum of object 2, don't worry about this yet, will actually be equivalent to the total momentum before. That's this comment over here. So you have to recognize P before is for a system now. This is for a system. This is total. Put a little word over here, system. So however many objects are in the system, that's how many terms you need down here. If it's 3 things, you would have P1 plus P2 plus P3. We will generally do 2 things, 2 objects, so it makes it easy. After the explosion, there are still cannon and ball, 2 objects. And so after the explosion, we have momentum of object 1 plus momentum of object 2 is equivalent to the system momentum after, the total momentum after. Finally, just substitute. We know that P equals mv. So momentum of object 1 is m1v1. Momentum of object 2 is m2v2. These are on the before side. After is m1v1 plus m2v2. And these are on the after side. Now, I know this looks very similar. Like, wait a minute, we're writing the same junk on both sides. Yes, we are. So wait a minute, the whole left side should be equal to the whole right side. Yes, it is. Oh, so wait a minute. That this M1V1 is the same as this M1V. No, it's not. No, it's not. Do not make that mistake. And that's where the word before and the word after comes in so critically. You must think about before the explosion and after the explosion. Before the explosion, yes, the objects each have their masses and they have particular velocities. After the explosion, yes, they have their masses, and they will have different velocities than they had before. So there is difference here. Okay, just as a reminder, Newton's third law connection, you can do this same problem. Don't sweat it now, but you can do this same problem using delta P1 equals negative delta P2. This would actually work as well, but hold off on for that for right now. In fact, Newton 3 connection, we'll pull that up in just a second. All right, let's come over here. We're not going to look at the collision side. We will look at the explosion side for right now. Before an explosion in our course, both objects will be at rest. That makes this before side really easy. That's V1 is 0 and V2 is 0. Makes it really easy. Still, I want you to substitute. Before an explosion, both objects have 0 momentum. Of course, if they're at rest, they have no momentum. Therefore, the total momentum is 0. This is before. Let's not mess this up. Before. Finally, since P before equals P after an explosion, if it's 0 before, after it must be 0 as well. However, that means this term up here is 0, but these individually do not have to be 0. One has to be positive, one has to be negative, and then they sum up to 0. Okay? Now, in general, here's a good comment. In general, the object with the greater mass will have the smaller change in velocity. This is a big comment right here because this one's for your intuition. This one is for your intuition. If you get this right with your intuition, you will be more comfortable with these problems. We looked at 2 examples yesterday. Here was that lady with the gun. Here is that guy with the cannon. Both of these were recoil scenarios. And in both of these, the person got, well, this one probably got a lump, and this one, I don't know. He may be very hurt. Anyway, what happened here is you had a gun. Let's just draw a block. The gun was here, and the bullet's here. Now, the bullet fires forward. The gun fires backward. The gun has a big mass. the bullet has a little mass. Not surprising, the bullet has a big velocity and the gun has a little velocity. Sorry, I drew this one wrong. Big velocity, little velocity. Of course, the bullet is in the forward direction. We can call that positive. The gun is in the backward direction. Maybe we call that negative. And if you notice here, big M times little v will match little m times big V. That's the conservation of momentum. That's why the gun came back and hit her in the head. Of course, the gun did not come back nearly as fast as the bullet went forward. If it did, her head would be in very different condition. Even here, this big mass cannon came backward at a small velocity, big mass, but the bullet they put into it went forward at a big velocity because it had a relatively small mass. This actually is exactly from the little extra note I wrote for you yesterday when we were breaking down Newton's third law, all the different versions. It's from this one right here, right? If we rewrite this one the same way that we rewrote the MAs when we did the ball throw, the medicine ball throw, you would say the little mass will have a big change in velocity, whereas the big mass will have a little change in velocity. Okay? And that, of course, makes sense. That is why guns must be heavier than bullets. If bullets are heavier than guns, we start to have a problem there. Then the gun actually moves off with a greater velocity than the bullet. And you're supposed to be holding that. Anyway, that brings you to the next page, and there'll be a next video.